You paste a massive document into your local 70 billion parameter model. You hit generate, and then the generation speed silently stalls in half. You check your task manager. Your VRAM is redlining. That isn't a driver glitch. It isn't a bad graphics card. It's the KV cache and runtime overhead silently eating your budget, long before the model weights even finish loading, turning a perfect fit on paper into a choking bottleneck. This is how to size VRAM for local LLM inference in 2026. You'll learn why static charts lie, how the KV cache and quantization actually drain memory, and the calculator method to pick the right GPU without wasting cache. First, the KV cache trap. Second, the reality of quantization and moe models. Third, the calculator rule for sizing your rig. Because if you ignore these hidden costs, you'll buy a card that fits the weights but chokes on real usage, wasting hundreds of dollars on hardware you can't actually use, wasting time trying to run a model that barely fits, and watching it fail at the worst moment. You probably think VRAM just needs to scale linearly with parameter count, and that quantization is a simple byte per parameter swap that shrinks the model without side effects. But that's wrong, because the inference engine is a living process. It does work. It allocates buffers. It manages streams. It's not just a file sitting on a disk. Think of VRAM not as a storage closet for the model weights. Think of it as a dynamic workbench. The model weights are just the tools sitting on the shelf. But the KV cache, the context, and the runtime overhead are the expanding pile of papers you're actively working on. And that pile grows faster than you think. If you keep writing notes, the pile grows. You run out of desk space, you have to clear papers. But the model can't clear the KV cache. It needs to remember everything. So the pile keeps growing until the desk breaks. First, the KV cache trap. The KV cache is a dynamic buffer storing attention states for every token you process. It grows aggressively as your context window expands. Push it too far and your GPU stalls. Every new token locks up memory. You can't evict it. It's permanent for that session. Context is the main culprit. An 8,000 token window might look small on paper, but the KV cache stores keys and values for every single token. That memory usage scales linearly with context length. Double the context. Double the cache footprint. Tokenization matters too. One document might be 5,000 tokens, another might be 20,000. The cache doesn't care about words, it cares about tokens. Batch size adds more pressure. Larger batches demand extra space for intermediate activations, because every extra sample in your batch demands its own slice of memory, multiplying the load instantly. But here's where it gets weird. Quantization is a density tool, not a magic swap. You might compress the weights to 4 bits, but that math completely ignores the runtime overhead modern inference frameworks demand. Even when you compress weights, you still need breathing room. For the KV cache, system allocations, and the engine itself, according to Sphera Network, that overhead reportedly sits between 10 and 30% depending on your stack. Even small changes in your inference engine can push that overhead toward the 30% mark. CUDA kernels, memory fragmentation, and the inference loop all burn that buffer. A quantized 70 billion variant might comfortably fit on a single 40 to 48 gigabyte card, but only if you reserve that buffer. Treat quantization as a compression trick without accounting for overhead, and your system will thrash. Thrashing means your GPU swaps data to system RAM. Your speed drops from tokens per second to tokens per minute. We really need to view quantization as a density tool, not a magic fix. And treating quantization as the only factor is a trap. In a second, I'll show you the architecture that breaks the math entirely. Mixture of experts models lure you with the promise of efficiency. You might assume fewer active parameters per token means less VRAM. That's a trap. While moe-architecture's route computation through sparse subsets of experts, the GPU must still load the entire parameter set into memory, select and switch between them. Imagine a team of specialists. The model calls the right expert for the job, but the whole team has to be in the room. The VRAM budget doesn't care about active versus inactive parameters. It only cares about what's resident on the card. You might save compute per token, but you still need that massive card for the full weight footprint. moe models like Mixtral or Llama 3.1 moe have huge parameter counts, but only a fraction are active. Yet the VRAM usage matches the full count. This confuses everyone. You see low active parameters and think cheap GPU. you buy the cheap GPU. And it fails. Static sizing charts suggesting moe models require less memory are obsolete. In a moment, I'll give you the exact calculator rule that saves you from buying the wrong card. So how do you actually size your rig? The 2026 baseline demands a calculator approach, not guesswork. You'll typically see overhead and cash growth consume roughly 20% of your total budget before you even hit the weights. Here's the math. Take your model size, add 20%. If that number is under 48 gigabytes, you're good. If it's over, you need more memory or a smaller model. You can now run quantized 70 billion models on a single 40 to 48 gigabyte card, provided you strictly manage your context window and account for framework overhead. For smaller workloads, you'll still find capable local inference on lower-tier cards, but you need to track your batch size carefully. If you're building a workstation today, aim for that 40 to 48 gigabyte tier to handle heavy quantized models with reasonable context, or lean into tighter setups for efficient 7 to 13 billion inference with strict limits. The shift to models like Llama 4 and Qwen 3 means your old rules are dead. You need to calculate the complete memory equation before you commit to hardware. Static VRAM charts are dead. Sizing for local inference now means calculating the complete memory equation of context, cache, and architecture, ensuring your rig delivers throughput instead of choking on runtime demands. You'll stop wasting money on hardware you can't fully utilize. And finally, get the local inference experience you were looking for. We covered the KV cache trap, which grows with context and stalls GPUs, the reality of quantization and moe models, where active parameters lie, and overhead bytes, and the calculator rule, which demands reserving 20% for overhead to size your rig correctly. Treat VRAM as a living equation, not a static counter, and you'll stop wasting money on hardware you can't utilize and finally get the local inference experience you need. If you want this stuff explained without the hype, subscribe. That's what we do here, daily. That's the full picture. If this made it click, tap subscribe. There's a new AI explainer here every day, and tap the video on screen to keep going. See you in the next one.